Designing radio chips is so hard, engineers call it a dark art, and they mean that literally. It's not just difficult, it's the kind of work where experience, gut instinct, and years of trial and error matter more than any textbook. And right now, that bottleneck is slowing down everything from 5G to self-driving cars to satellite communications. These chips are called RFICs, radio frequency integrated circuits. They're what let your phone talk to a cell tower, what lets a car's radar sense objects nearby, what lets a satellite dish lock onto a signal from orbit. Every wireless device you use depends on them. The problem is getting them right takes an enormous amount of specialized knowledge, and even then it can take months or years to go from an idea to a working design. The reason it's so hard comes down to physics. When you're working at radio frequencies, everything interacts with everything else. A tiny change in one part of the circuit ripples through the whole thing in ways that are incredibly hard to predict. You're not just drawing connections on a chip, you're sculpting electromagnetic fields, and the tools engineers have used for decades weren't really built for that level of complexity. They help, but they don't solve it. So researchers at Princeton decided to try something different. Instead of helping engineers design chips faster, they asked a different question. What if you let the AI design the chip from scratch? They use two approaches, and both of them are worth understanding. The first is reinforcement learning. You've probably heard of this in the context of game-playing AI. It's the same basic idea. You give the system a goal, let it try things, reward it when it gets closer, and let it figure out the path on its own. In chip design, the goal is something like minimizing signal loss, or maximizing power efficiency, or hitting a specific frequency target. The AI doesn't start with a human template. It explores the design space on its own and finds configurations that engineers wouldn't have thought to try. The second approach uses diffusion models. If you've used AI image generators, you've seen diffusion models at work. They learn the underlying patterns in a dataset and then generate new examples that fit those patterns. Applied to chip design, they can take a performance target as input and produce a circuit layout that achieves it, not a modification of an existing design, a genuinely new layout generated from scratch that meets the spec. What came out of this research is remarkable. The AI produced designs that hit record-level performance numbers, not just competitive with the best human designs. Better than them in some cases, and it did it in a fraction of the time. We're talking about cutting design cycles that used to take months down to hours or days. There's also something interesting about how these AI designs look. Some of them are completely alien, geometries and configurations that no human engineer would have drawn because there's no obvious intuition behind them. They work, but you couldn't easily explain why just by looking at them. That's a little unsettling, but it's also a sign that the AI is genuinely exploring new territory rather than copying what humans already do. But other designs from the diffusion models are actually interpretable. A human engineer can look at them, understand what's happening, and learn from them. That's important. It means AI isn't just producing black box solutions. In some cases, it's producing solutions that teach us something new about how these circuits work. Now here's the part that matters for where this goes next. AI learns from data. The better and more diverse the training data, the more capable the system becomes. Right now, chip design data is largely proprietary. Companies guard their layouts, their performance measurements, their design history. That means any AI trained today is working with a limited view of the problem. For this technology to really take off, the field needs shared datasets. Open repositories of chip designs that researchers everywhere can use to train better models. That's a big cultural shift for an industry that's built on secrecy. But it's the same shift that happened in other fields, like computer vision or natural language processing, and the results were transformative. The analogy that comes to mind is software. For decades, professional software development was also a kind of dark art. You needed experienced people who had seen enough problems to know the patterns. Then better tools came along, then open source, then AI assistants. It didn't eliminate the need for good engineers. It changed what those engineers spend their time on. The same thing is likely to happen here. Instead of spending months hand-tuning a circuit layout, RF engineers might spend their time setting targets, evaluating outputs, and pushing the boundaries of what's possible, the creative and strategic work. The AI handles the exhausting search through an enormous space of possible designs. For the rest of us, the implications are real. Better RFICs mean faster wireless networks. They mean radar systems in cars that are more accurate and cheaper to produce. They mean satellite links that are more reliable. They mean medical devices that communicate with less power and less interference. A lot of the wireless future people talk about is bottlenecked by chip design. Removing that bottleneck matters. We're not at the point where every company can just type in a spec and get a perfect chip back. The research is early. The datasets are thin. The tools aren't fully productized yet, but the proof of concept is there and it's strong. AI can navigate the dark art of RFIC design. In some cases, it's already doing it better than the people who invented the field. That's worth paying attention to.